In the previous session, it was discussed about the analytical methods to estimate the bearing capacity of soil. So the other methods are field tests. Using the field tests also we can estimate the bearing capacity of soil. So the different field tests which can be used to estimate the bearing capacity are standard penetration test, plate load test and cone penetration tests. So in the standard penetration test, a borehole will be excavated to the desired depth. Then the split spoon sampler will be inserted into the soil using the drop hammer. So the number of blows required for 15 cm drive will be counted and the procedure is repeated for another 2 drives. So total 45 cm drive, the number of blows required will be counted. The first 15 cm drive will be neglected and the number of blows required for the next 2 drives, that is for a drive of 30 cm, will be taken as standard penetration number. Sometimes when a very soft stratum is there, then the sampler may simply sink into the soil under its own weight. So under such conditions, we should take the standard penetration number as 0. And if the number is exceeding 50, then we should take it as refusal and the test is discontinued. So after finding the N value, we have to apply 2 corrections to the N value, that is the overburden pressure correction and dilatancy correction. So in the overburden pressure correction, the number has to be multiplied with the normalizing factor, which is equal to 0.77 log to the base 10 2000 divided by sigma naught dash. So here sigma naught dash is the effective overburden pressure which has to be taken in kilonewton per meter square. Then if the soil is sandy soil and if it is submerged, then we should also apply the submergence correction. So here when the N value is greater than 15, this is the N value obtained after the overburden pressure correction. If that value is greater than 15, then we should take the corrected N value as 15 plus half into N naught minus 15. And if it is less than or equal to 15, then we can take the corrected value as that of the value obtained after overburden pressure correction, that is N naught. So there are some correlations available to estimate the shear parameters, that is phi value from the corrected N value. So from the corrected N value we can find the phi value and then we can find the bearing capacity factors from the table, either in the Terezagis method or Reyes code method. We can find the bearing capacity factors and then by substituting in the analytical solution of bearing capacity, we can calculate the bearing capacity of soil. And Tang has given some direct correlations to estimate the net ultimate bearing capacity for strip footing as well as square or circular footing. So for strip footing, the equation is given as 1 by 6 3n square b into rw2 plus 5 into 100 plus n square drw1. So here in this equation, n is the corrected n value, corrected standard penetration number, and d is the width of the footing, and rw1, rw2 are water table correction factors. So here the value will be obtained in kilonewton per meter square only. And for square or circular footing, the equation is given as 1 by 3 into n square b rw2 plus 3 into 100 plus n square d rw1. So using these equations directly we can calculate the net ultimate bearing capacity. Indirect method is we can use these correlations. We can find the phi value for the corresponding n value from the table and then we can use the normal Terezagis or Reyes code method to estimate the bearing capacity. That is one way of finding the bearing capacity. So here the advantage with this field test is we can estimate the bearing pressure also using the analytical methods, we can estimate only the safe bearing capacity, which is related to the shear failure criteria. But here, using the field tests, we can also estimate the safe bearing pressure, which is related to the settlement criteria. So based on the settlement criteria, also we should estimate the bearing capacity, and then we should take the smaller one as the allowable bearing pressure. So Bowles equation is available to estimate the safe bearing pressure, which is equal to S by 25 into 52.5 into n minus 3 into B plus 0.3 by 2B square RW to FT. So here in this equation, S is the allowable settlement. And this value we should take it in millimeters, because this 25 mm is taken in millimeters. Then this is the corrected end value. B is the width or diameter of the footing. Then here FD is the depth correction factor, which is equal to 1 plus 0.2 d by b, where d is the depth of the footing and d is the width of the footing. And RW2 value is 0.5 into 1 plus ZW2 by b. So here, after finding the safe bearing pressure and net safe bearing capacity, we can take smaller of these two values as the allowable bearing pressure. Design a square footing to carry a working load of 900 kN with a factor of safety of 3. The depth of footing is 1.5 meter below the ground level. The water table is at the base of the footing. The unit weight of soil above and below the water table are 17.5 and 20 kN per meter cube respectively. The corrected end value and allowable settlement are given as 29 and 25 mm respectively. So here corrected end value is directly given, which is 29. So we can calculate the net ultimate bearing capacity, and since it is square footing, we have taken this equation which is given by Teng. Then here when we substitute the values of N, B, RW1 and RW2, we'll be getting the net ultimate bearing capacity in terms of B. Because B is not given, we should take it as a constant B. Then we'll be getting the equation in terms of B. So we should calculate the net safe bearing capacity in terms of B, and then we should equate it to 900 divided by B square. So this is the safe load divided by, we'll assume this is the net safe load divided by area of the footing, because it is square footing, area is B square. So then we will be getting one equation in terms of B. Then we can calculate the value of B. So this is based on the shear failure criteria. Based on the shear failure criteria, the width of the footing is obtained as 1.1 meter. Then we should calculate the width of the footing based on the settlement criteria. So the equation is S by 25 into 52.5 n minus 3. This is the Bowles equation. So here we should calculate the depth correction factor first. So since B value is unknown, we'll be getting in terms of B. And then the equation will be in terms of B only. And when we equate it to the safe load divided by area, we'll be getting the B value as 1.85 meter. So this is based on the settlement criteria. So based on the shear failure criteria, width of the footing is 1.1 meter, and based on the settlement criteria, the required width of the footing is 1.85 meter. So we have to provide the higher dimension to take care of both the shear failure as well as settlement failure. So that will be 1.85 meter. Another example is a square footing is required to carry a net load of 1200 kilonewton. Determine the size of the footing if the depth of the footing is 2 meter and permissible settlement is 40 millimeter. Soil is sandy with corrected end value is 12. Take factor of safety 3. Water table is very deep. So from the shear failure criteria, by taking the Teng's equation, we will be getting the width of the footing is 2.45 meter, and from the settlement criteria of Bowles equation, we will be getting the width of the footing is 2 meter. We will be taking the higher dimension as the size of the footing, that is 2.45 meter. Next example is design a square footing to carry a working load of 1000 kilonewton with a factor of safety of 3. The depth of footing is 1.5 meter in a sandy soil. whose average SPT is 15, gamma equal to 18 kilonewton per meter cube. Water table is at a depth of 2 meter below ground level. Estimate the expected settlement of the design footing using corrected N value. So here two things are asked. One is to find the width of the footing and the other one is to find the settlement, allowable settlement. So we can use the net ultimate bearing capacity equation to estimate the width of the footing, and by substituting this value in the bearing capacity and bearing pressure equation, we can estimate the settlement. So here the value N value is not the corrected one. So this N value is given as SPT value is 15. This is the field value. So we have to find the corrected N value. For that, first we have to apply the overburden pressure correction. So for the overburden pressure correction, we need to estimate the effective overburden pressure, which is equal to depth of the footing is given as 1.5 meter and unit weight of soil is 18. So effective overburden pressure at the base of the footing is 27 kPa. Then by taking this 27 kPa in the normalizing factor, and when we multiply with the N value of the field test, then we will be getting the corrected N value for the overburden pressure. Then here because it is sandy soil and because it is submerged, we have to apply the submergence correction also. So here the N value is greater than 15. So we should use the equation 15 plus half into N0 minus 15. From that we will be getting the corrected N value as 18.3. So then we have to round it to the nearest integer. So we can take this value as 18. And we have to take the Tanks equation where the net ultimate bearing capacity for the square footing is given as 1 by 3 into n square into b into rw2 plus 3 into 100 plus n square drw1. So in this equation, when we substitute the value and then by finding the net bearing capacity in terms of B, we can calculate the B value by equating this net bearing capacity to the load divided by area. We will be getting one equation in terms of B. By solving that equation, we can estimate the width of the footing. Then we should take the Bowles equation where settlement is there, and by taking this B value in this equation, we can estimate the settlement. So here bearing capacity, bearing pressure can be taken as 100 by B square. So B value is obtained from the first equation, and by taking this value in the second equation, we will be getting the settlement. Next topic is foundation settlement. So the foundation settlement is broadly classified into two types: total settlement and differential settlement. Total settlement is the sum of immediate primary consolidation and secondary consolidation settlements. Immediate settlement. The settlement taken place immediately after the construction of a structure is called as immediate settlement, which is given by Q into B 1 minus mu square by ES into IW. So here Q is the intensity of uniform pressure which is acting on the footing, and B is the least lateral dimension of the footing, mu is the Poisson's ratio of soil, and ES is the modulus of elasticity of soil. And here IW is the influence factor. So by taking all these values and substituting in this equation, we can estimate the immediate settlement. So immediate settlement happens only due to the expulsion of air from the soil in case of clay soil, and this happens due to the expulsion of air as well as water in case of granular soil. So primarily this immediate settlement is happening due to elastic adjustment of particles. Then the second one is consolidation settlement or primary consolidation settlement. So this occurs due to gradual expulsion of water from the voids of soil, and it can be estimated using the equation Cc into H0 by 1 plus C0 log to the base 10 sigma naught dash plus delta sigma dash divided by sigma naught dash. Here Cc is the compression index. If the value is not given, then we should estimate it indirectly using the liquid limit value, which is equal to 0.009 into liquid limit minus 10% for undisturbed soil, and it is equal to 0.007 into liquid limit minus 10% for disturbed soil. And here H0 is the initial thickness of clay soil, E0 is the initial water ratio of the clay soil, sigma naught dash is the initial effective overburden pressure at the center of clay layer, delta sigma dash is the increase in effective stress at the center of clay layer. So here sigma naught dash is the geostatic stress, which is due to sulfate of soil, and delta sigma dash is the increase in stress due to external load such as foundation. Then secondary consolidation settlement. After the complete expulsion of water from the voids, there are also some settlements takes place due to the expulsion of double layer water and also the plastic readjustment of particles, which is called as secondary consolidation settlement. This is equal to Ca into H into log to the base 10 T2 by T1. So here Ca is the coefficient of secondary consolidation, which is given as delta E by 1 plus Cp into 1 by log to the base 10 T2 by T1. So here delta E is the change in void ratio between time T1 and T2. That is the time after primary consolidation and at the end of secondary consolidation. Ep is the void ratio at the end of primary consolidation. Then this can be also written as delta E by 1 plus Cp into H. So after calculating all these three settlements, then we can estimate the total settlement, which is the sum of immediate primary consolidation and secondary consolidation settlements. If it is a granular soil where there is no consolidation settlement, the total settlement equal to immediate settlement. Whereas for clayey soil, the total settlement is the sum of these three settlements. Another type of settlement is differential settlement, represented with symbol delta. So if there are two adjacent columns subjected to different loading, then the difference between the settlements is called as differential settlement. So here differential settlement equal to S1 minus S2. So here S1 is the settlement under column 1 and S2 is the settlement under column 2. The difference between these two settlements is called as differential settlement. Then tilt or angular distortion is the ratio of differential settlement to the spacing. If the spacing is L, delta by L is called as tilt or angular distortion. If it is a raft footing, then angular distortion equal to differential settlement divided by maximum settlement at the center. And this differential settlement should not be greater than 3/4 of total settlement for footings, and it should not be greater than 37% of total settlement for rafts. So these settlement values, allowable or permissible settlement values, are given in IS code IS 1904 for different types of footings and for different types of soils. So after calculation of the settlements, we have to check with the allowable limits given in the IS code. If the values are exceeding, then we have to redesign. We have to change either the width of the footing or depth of the footing, or we have to change the type of the footing, or sometimes we have to increase the bearing capacity of soil, or we have to increase the strength of the soil using some ground improvement techniques. This is one example. A 6-meter thick bed of clay is overlain by 9-meter thick layer of sand with water table at 4 meter below the ground level. Liquid limit is 43%, specific gravity is 2.7 and natural moisture content is 39%. The unit weight above and below the water table is 17.5 and 21 kN per meter cube. Calculate the settlement of a building constructed on sand layer if it causes an increase in effective vertical stress of 140 kN per meter square at the middle of clay layer. So here two layers are there, sand layer and clay layer, and it is asked to estimate the consolidation settlement. Since the consolidation settlement happens only in clay soil, so we have to take the properties of clay soil only. And for sandy soil, above the water table, the value is 17.5 kN per meter cube. Below the water table, we should take the submerged unit weight, so which is equal to saturated unit weight minus unit weight of water. And for clay soil, since the degree of saturation is 1 because it is below the water table, we can find the void ratio as the product of water content into specific gravity. So here water content and specific gravity are given 0.39 and 2.7, so that we can calculate the initial void ratio. Then we can also calculate the submerged unit weight from the equation G minus 1 into gamma W by 1 plus E. Then we have to calculate the initial effective overburden pressure at the center of the clay layer. From the ground level to the center of clay layer, we have to calculate the effective stress. So for the top layer, that is for the first 4 meter thickness, the unit weight is 17.5. For the remaining 5 meters, it is 11.19, that is the submerged unit weight. Then up to the center means 3 meter. 3 into your submerged unit weight is 8.123. So we can calculate the initial effective overburden pressure from the unit weights. Then we need increase in effective stress is given, which is 140 kN per meter square. So delta sigma dash is given, sigma naught dash is calculated. Then H naught is nothing but thickness of clay layer, that is 6 meter. Then E naught value is calculated, which is 1.053. And CC value, compression index. Since it is undisturbed soil, we can take the equation 0.009 into liquid limit minus 10, so that we can estimate the compression index. By substituting all these values in the equation, we can estimate the settlement of soil. Since we have taken the H naught value in meters, we will be getting the answer in meters that can be converted into millimeters. Another example is estimate the settlement for a column footing 1.5 meter by 1.7 meter in plan at a depth of 1.2 meter below the ground level. The properties of the soil are Cc equal to 0.1, E naught equal to 0.85, gamma equal to 14.5 kN per meter cube, and submerged unit weight is 9.5 kN per meter cube. The water table is at the base of the footing. The load on the column is 500 kN and the thickness of clay layer below the footing is 3 meter. So here also we should calculate the value of sigma naught dash at the center of the clay layer. So for that we should find the unit weights. So here unit weights are given for each layer. Here it is 9.5 and here it is 14.5, and water table is at the base of the footing. So for the top layer, the unit weight is 14.5. So 1.2 into 14.5 plus here the thickness is at the center of the clay layer means, so the thickness is 1.5 into submerged unit weight is 9.5. So from this we can calculate the initial effective overburden pressure at the center of the clay layer. Then here delta sigma dash value is not given, but here the total load that is coming onto the footing is given, which is 500 kN. So using the 2:1 method, 2:1 approximate method, we can estimate the increase in stress. So where the increase in stress equal to total load divided by load on which the area on which load is acting. At the center, the area on which the load is acting is B plus Zi into L plus Zi. Zi is the depth from the base of the footing. So from the base of the footing to center of the clay layer, it is 1.5 meter. So by taking Zi value as 1.5 meter, we can calculate the increase in stress, that is delta sigma dash. Then we can substitute in the equation of settlement, and then we can calculate the settlement. This is also similar problem. So here the soil profile is given, and it is having sand layer and clay layer, and the footing is at a depth of 1 meter in the sand layer. So here we should find the settlement of clay layer, for which we should calculate the sigma naught dash and delta sigma dash values. So to calculate the delta sigma dash value, because it is a square footing, we can use the equation Q by B plus Zi square. So here Zi value is from the base of the footing to center of the clay layer. So this is 4, and this is 4 meter plus this is 1 meter. So it is 5 meter. Width of the footing is 2. So 2 plus 5, it is 7 meter. So that will be getting the delta sigma dash value. By substituting these values in the equation, we can calculate the consolidation settlement. This is also a similar problem. So here also 2 layers are given. We have to calculate the sigma naught dash and delta sigma dash corresponding to center of the clay layer. So here E naught value is also given, and CC value is also given. So we can directly substitute in the equation, and then we can estimate the consolidation settlement. Another example is related to immediate settlement. So in this problem, the size of the footing is given as 2 meter by 3 meter, and depth of the footing is given as 1.5 meter, and compression modulus is given in Newton per millimeter square. So we have to convert it into kilonewton per meter square. So here footing is expected to transmit a unit pressure of 200 kPa, that is Q value is given as 200 kPa. Poisson's ratio mu is given as 0.3. Influence factor, that is IW, is given as 1.06. So here directly we can substitute all the values. Here B is the least lateral dimension, so we should take it as 2 meter. Then all other values are given. Only thing is we have to convert this Newton per millimeter square into kilonewton per meter square. And when we substitute all the values in the equation, we will be getting the settlement in meters, because B value we are taking in meters, we will be getting the answer also in meters. Then we can convert it into millimeters.